When physicists derive massive, complicated equations, a single mathematical error can mean the difference between a satellite reaching orbit or crashing back to Earth. They need a reliable way to spot a bad formula before a single piece of hardware gets built. The quickest check relies on a strict rule of physical reality. You can only add or subtract quantities that share the exact same physical nature. You cannot take 3 meters of length and add a unit of force to it. You cannot subtract 5 amps of electrical current from an ambient temperature. The math simply refuses to compute. This boundary is known as the principle of homogeneity of dimensions. To use it, physicists strip an equation down to its barest mechanical components. They reduce the variables to the big 3 base dimensions: mass, length, and time. By translating complex mathematical variables into these simple base dimensions, we create a strict filter. If the dimensions on either side of an equation do not match up perfectly, the formula is physically impossible. Let's test this failsafe on a standard kinematics formula, the equation used to calculate the distance an object travels over a period of time. We start with the position variables, the final position x and the initial position x sub 0. Regardless of whether we are measuring millimeters or light years, their base dimension is simply length. Next is the velocity term. Velocity is defined as a length divided by time. When we multiply that by our time variable, the units of time cancel each other out, leaving us with another unit of length. Finally, we deconstruct the acceleration term. Acceleration is a length divided by time squared. Multiplying that by time squared means the time elements are completely erased. We are left with one final unit of length. Because every single chunk of this mathematical expression reduces independently to the exact same dimension, we know the equation is consistent. It passes the test. We can push this further by comparing 2 seemingly different physical states across an equal sign: kinetic energy and potential energy. On the left side, we have kinetic energy. When we take mass and multiply it by velocity squared, the individual dimensions combine into a highly specific signature: mass times length squared times time to the power of -2. Now look at the right side, potential energy. This is calculated by multiplying mass, the acceleration of gravity, and height. Break those variables down to their base components, and we arrive at the exact same dimensional signature, a perfect match. This proves that a moving object's kinetic energy and a resting object's potential energy share the exact same physical nature. That is why they are allowed to balance at an equation. Both of these tests worked flawlessly, but if you look closely at those deconstructions, a critical piece of information quietly vanished during the process. Look at the fraction 1/2. It appears in the formulas for both kinematics and kinetic energy, yet our dimensional check completely ignored it. This exposes the primary blind spot of the failsafe. Pure numbers, ratios, and mathematical constants do not possess physical dimensions. To this type of analysis, they are entirely invisible. As a result, you could write down a formula full of wildly incorrect numbers, and the dimensional test would still approve it as a valid expression. For instance, a formula claiming kinetic energy is equal to 3/16 times mass times velocity squared shares the exact same flawless dimensional signature as the true formula. This establishes the definitive rule of the failsafe. If an equation fails a dimensional test, it is 100% incorrect and physically impossible. But if an equation passes the test, it is only dimensionally possible. Passing does not guarantee that the formula is the exact truth. Dimensional consistency is a necessary filter for weeding out bad math, but equations alone aren't enough. To find the missing numbers and confirm the truth, physics relies on hard, real-world experimental verification.